But what would you go for?
Hair color.
Hair color, not bad. Okay. Do you think it's better to ask about hair color itself, or something like dark color, light color? You would go?
Male, female.
Okay. Yes. This is like a fairly antiquated board. So it's like very binary. So in general there is a recognizable binary gender, male, female, hair color. Yes, like dark or light. What else? Oh.
Do they have glasses?
Do they have glasses? There's also a decent one. How about, does it have a green hat? Is this a good question or bad question? Not really good. Why? It's too specific. That's a good point, right? Because it's a kind of question where in one case, there are, I think, 24 characters on this board. So in one case, you learn a lot, right? But with a high probability, you don't really learn too much. So the idea here of decision trees, and guess who, is that this algorithm consists in a set of questions. They give you. So now with the set of questions, should this agree with set or with questions? A set of questions gives you the answer or give you the answer? Gives. Okay. Very good. I also need to learn something, so hey. And of course, you don't just want the answer, you want it fastest there. Just fastest. Right? So the goal is to come up with a set of questions that you want to ask so that you get your answer as efficiently as possible. And by the way, this is a supervised learning method. And supervised learning method means two things. One is that we predict a quantity for each example. Like in the case of guess who is like the identity of your subject. The other thing is that we learn by example. So we need to have a subset of objects for which we know what the answer is. Okay? So this is just like the real of the method. Now, how does it work? How do I build a decision tree? The main idea is that just like in guess who, I have to make binary splits. This is not, a necessity. This is just, sort of like a convention of how they work. So I have to ask a question about the input variables, or, in machine learning jargon, these are called features that I have. So I can split my data in two partitions according to the value of that feature. And let's see. So let me give you an example. So this is, sorry for the sort of color. I want to make binary splits on the features that I have. The features is another name for variables. Okay, so let's say that I will make a star galaxy separator. So these are, say that I have a very simple data set. I have two features. Let's put some stars here. Okay, and then we also put some galaxies. I'm going to make them spirals, so I'm going to make them blue. Okay. Does this work? Kind of. Okay. Sorry, these are clearly spiral galaxies, as you can see. All right, so my goal is to ask some questions, or in other words, make some binary splits so that I can separate efficiently these two classes of objects. And the trick is there that I'm only allowed to make splits on the features that I have, in this case, x1 and x2. So all the splits that I make need to be parallel to the features that I have. So what do you think? What should I ask as my first question? To create these partitions.
Is x2 above some value?
Is x2 above some value? Very good. So, we want to sort of have this split properly, probably. So let me say that this is 0, 1, and 0, 1. So maybe a good question to ask is x2 greater or equal to 0.5? Okay. And then, I have to make my split. And so this means that I have to distinguish, am I going to say yes or am I going to say no? All right, let's say that I say no. What should I do then? Am I ready to predict something? If x2 is less than 0.5? Yeah, what do I predict? Galaxy, excellent. All right, so at this point I can do my prediction. And if x2 is greater than 0.5, maybe I should ask another question. What question can we ask?
X1 above 0.75.
Very nice. Is x1 above let's say 0.75? Greater or equal than 0.75. And then at this point, I want to keep my direction with yes being left and no being right. And then if the answer is yes, what should I predict? Galaxy. And if the answer is no, star. Right? So you just built a decision tree. So once again, like all that you need is to decide which split you're going to make that are parallel to the features. And of course, you want something that is somewhat efficient. Now, in a data set that is bigger than this, with more than 2 features, you cannot really plot it and decide by hand, just by checking in what kind of splits you will want to make. And so the way that this works for larger data set is a few steps process. I haven't counted it. So first, you consider all possible splits that are parallel to the features you have. Right? So if you had many features, you would say, okay, in all of them, I can split in many ways. Of course, formally, the number of splits is infinite, right? Because you're looking at a continuous space. But in general, you can imagine that you can make the ones that, sort of straddle one object's equivalent to each other. So effectively, you are, quantizing your space. So you're looking at the finite numbers. So you look at all the possibilities. Then the next thing, of course, is that you have to choose which ones you're going to make. Right? And so you need some sort of a fitness criterion for the splits. And what do you think we should do? What makes a good split? Why did we choose this one here instead of this one, for example, or this one?
High entropy gain.
High entropy gain. Oh, this is too complex. Okay, yes. Here. But yes, okay. But in simpler terms, what we're trying to do, what does this split do that this one doesn't? It creates a partition that is homogeneous, right? And this is desirable. Now, I could have made a partition that is homogeneous in many ways. For example, I could have split here. Why was this better than this?
Maximizes purity.
Right, maximizes purity. But if you look at this one, this is pure 100%, and this is pure 100%. So why is this bigger? So why is this better?
It's sorted more at once. It's sorted more at once correctly.
Is sorted more at once correctly, right? So basically, what we're trying here is that we choose, like a good split is a split that maximizes the decrease of impurity, which is another words of saying we are maximizing the purity of the resulting partition. But the other thing that is important is the volume, or like the size of the partitions that we make. So our fitness criteria, we want to do, it's easy to take out tiny parts of a data set that are completely homogeneous, right? But still, if I do it, one by one, it's going to take me forever. So the idea here is that we want to have splits that maximize the decrease of impurity. And this is basically the product of size of partitions times, let me call it delta I, right? The purity of the resulting splits. Actually, let me write it down. Times the purity of partitions. So there is, like a price given for, how homogeneous the splits, the partitions are, and the prices is given for how big they are. And so this way, after considering the splits, very simply, I choose at each step the best one, right? It's like very unsophisticated. And then at some point, this could be enough. The one thing that perhaps is good to keep in mind is that maybe sometimes you can find yourself in a situation like this, right? So your data set is not exactly separable, or it could be, because I could actually keep making tiny splits parallel to the features, right? This is allowed, and I could have this object in its own little box. Would this be a good idea? What do you think? No, I say some no, but why? Is this
Overfitting.
right? Overfitting, which is the process in which we don't want, we want to learn sort of basic robust properties about data. In this case, stars and galaxies, which means where are they in this feature space? But of course, real data are full of statistical fluctuations or noise or failures. And so we may consider the options that, like an object that is here for some reason, despite being surrounded by galaxies, in fact, a star. But it's much more likely that this is just, a random fluctuation. And so because of this, I don't really want to continue maybe until all the partitions that I make are completely homogeneous, but I may want to consider a stopping criterion. So I may decide that my stopping criterion is infinite purity, or maybe this is better written as zero impurity, which means all the partitions I have made are perfectly homogeneous. But it could also be good to consider just a small value. So now I'm willing to tolerate some impurity in the splits that I make in return for more robustness, or more simply, a simpler algorithm. Like here, I did this with just like 2 splits, which is like very simple. And in general, as simple is desirable and tends to be more robust. To isolate this object, I would have to make 4 more decisions. Okay, now that you know everything about decision tree, now you have a challenge, because of course you didn't think that you'll be here doing nothing while I'm here doing all of this work of writing on the boards. Also, I need time to erase. So now you're going to make your own decision tree. I hope you brought pen and paper. I did say it even in the title. And so I'm asking you to come up with questions that are parallel to the features that you have. And let's see, I have, I don't remember, I didn't want to be too optimistic with audience, so you might have to share in two. But basically what you have here is a data set. These are real planets. And yay, planets, exactly. And we're trying to predict whether planet is habitable or not. So there is a label here where 0 means not habitable and 1 means habitable. And I'm giving you 3 features or inputs: the stellar mass in solar units of the star the planet is orbiting around, the orbital period expressed in days, and the distance expressed in astronomical units. Okay, so I'm going to give you 10 minutes, and I'm going to see if you guys can come with a good decision tree. Okay, so this will be a set of questions that predicts the correct answer. So there is a training and there is a test. And here. Okay, so I'm going to distribute some. If you guys want, first I've seen this before. You know, I'm gonna put one here. And let's see, maybe you guys can help me distribute some. Oops, on this. Do you mind passing one every 2 and passing it around? And then we'll see who can make the best tree.
Oh,
Yeah.
I keep in mind only binary splits and no combining features. Uh-huh.
yes, it's like So we have to like. Yeah, this is so hard.
That's why we use computers. Of course it's hard.
Where did you get the data?
The Planet Habitability Lab.
Yeah.
But I chose them,
Just like recently, I'll show you the notebook. I'll show you the notebook, but like recently.
It's true. Ari just suggested a new colloquium style that means you come in, you give people a task, you leave. You move on to the reception. All right, folks, I love this, but sadly, we have to continue. So let's see. Is anybody feeling confident about their tree? Yes, go ahead. What's the first question you would ask?
I think that if you say is the stellar mass
Is the stellar mass
greater than 0.82?
okay? We're all good in asking questions. Then what do we do?
If it is greater than 0.82,
Yes.
then it is not habitable.
Okay, so let me do what I can't remember the convention I used. So if a yes, not habitable. Okay.
If it is less than 0.82,
Yes.
that's a decision, and that's going to be on distance 80.
Okay.
And if it's less than 0.32 or 0.032, 0.032.
Less than
If it's less than 0.032, then it is also
0.032.
then it is also not habitable.
So if yes, not habitable.
Yeah. And if no, it's habitable.
Okay. Well, I can't verify this directly. However, the test, yes. Okay. Okay. Let me get there. So if you put this into sklearn, the first question is, in fact, is the mass greater or equal, or actually smaller or equal than 0.83? So I suspect that this is pretty cool. And if the answer is no, it's not habitable. So good job there. The other split is on orbital period. However, do you suspect that there is possibly a relation? No, Jared, sorry, I forget. This distance and orbital period are clearly independent variables. So, okay. So I think this is a good tree. I will give you, I can give you the test, but unfortunately, even this on test only gets 60%. But if you want to look at the last 5 objects for which the labels were not given, they were 0, 0, 1, 0, 1. Okay, so 0, 0, 1, 0, 1. But it's not an easy one. Even the, we are training the algorithm with 13 objects, so fair enough. Okay. Okay, now, however, so I have a question for you, which is, you all build these trees. Some of them do well, some of them they may not do well. So now here's a question for you. If we average the predictions of all your trees, would it be better or worse? Like, we're probably creative. We have like 23 years. I'm not going to try to do it now, I promise. But if we just took what the predictions are for all of your trees and we average them, and in this case, because it's a classification problem, average just means we take the majority class. Do you think that we will be more accurate or less? Or not sure? Less? Oh, more. Okay, I have 1 and 1. So the answer is, it depends. So I'll be very diplomatic. And so the idea is okay, let's say that, if you train n classifiers, that are independent, right? So in our case, we can assume they were independent, being different people. Then the probability of k of them being correct is something that has to do with the binomial distribution, which is permutation of n over k. Sorry, if you train classifiers, okay, and sorry, and each of them has a certain accuracy, p, let's say. Right, so this is like 60%, 70%, 80%, whatever you believe to be the probability that a single classifier is correct, and I'm assuming that they're all the same. So in this case, the probability of k of them being correct is n over k times p to the power of k times 1 minus p to the power of n minus k. Right, fair enough. I'm just like assuming that they're independent and put it together in probabilities. So the fact, we have that the combination classifier is correct when at least half are correct, right? Because we're taking the majority vote. So we need more than half of the classifier to be correct for the combined classifier with the average to be correct. And so this means that this, we can write it as the sum for I equal n half to n of n over I, p to the I, and then 1 minus p to the power of n minus I. In general, I try to stay away from math as soon as possible. Basically, this is just a cumulative probability that says, okay, if half of them or more are correct, I can sum all of these probabilities, and this is the total probability that the combination is correct. And you can actually show there is a bit of a trick where, like I did this like in Python yesterday just to check out some things. And, of course, I had the moment where I thought, okay, everything I've always known is wrong. But turns out I had just, misdefined the range of the variable. So I think there's a little bit of a trick when n is odd or even that I haven't solved. So there is some subtlety that I don't know. But essentially, this is greater than p when p is greater than 0.5. Which means that as long as your initial classifier is at least a little better than random, then the combined classifier will be better than the single ones. And so that's why I'm saying, yes, these are assuming they're independent and that their performance is the same. So of course, this is a big limitation, right? So this is just to see like why it would, overall, sort of like as a baseline works. So this is greater than p if p is greater than 0.5. So in this case, if we assume that, like all of us built a reasonably good tree, and then we average them all together, we get that the probability of the combined classifier to be correct is actually greater than the single one of each one of us. Okay, and this is, I should say, congratulations. What we just made here is an ensemble classifier. And the idea of ensemble is very powerful for these reasons, right? The whole idea is that you can start with what we call a base learner that is not very strong, but if you can combine them, then you can possibly, it's a possibility, I'm not even claiming, because it's what Mark was saying, like the details are more complicated than this, but this gives you a possible path to obtain something that is stronger overall. And now for our case, you all built independent trees, being independent people with your own brain and stuff. Like if we were to actually, build decision trees in the way that we have learned, and then decide that we want to combine them, we cannot really do this because the process that I gave you to build a tree is deterministic. Right? We look at all the possible splits, and then we choose the best split, and then we repeat until some criterion is satisfied. Right? So it doesn't, they're not independent, right? And because of this, combining them doesn't really give me anything. So what I need to do an ensemble in real life is some way of randomizing the tree. Like I need to make them independent somehow so that I can gain something from combining them. So let's see, how can we randomize these trees? Any ideas? There are at least 3 ways, possibly more than I don't know of, or at least 3 that are used normally, but I think in the end, you can do this in many different ways, as long as you are able to add some stochasticity to the output of the trees. So I don't know, any ideas? Subsample, very good. So one possibility is that, sorry, subsample the tree or the data?
Well, the variables or the variables and the data.
Excellent. When in doubt, always go for both. And in fact, in this case, they are both correct. So, right. So one thing is to bootstrap with replacement the learning set. Right? The learning set is the one that is used to build the model. So what I can do here, I have a collection of examples, and I can bootstrap with replacement with that. So I can make many copies. Every time I bootstrap, I pick one, and then I put it back. I pick one, and then I put it back. I do it for the same number of times as the number of objects in my data. I get something that is fairly similar, but of course, some objects may have multiple copies, some objects may be missing. And so this is one of the possibilities. The other one that I think we also mentioned is we can subsample the features. And so in this case, I can only split or find the best split on a random subset. So rather than considering all the possible splits in all the possible features, at each step I decided I'm just going to look at the set of this random subset of features and choose the best split in those. Another one that is perhaps less known is a bit more extreme, which is after I select the features that I'm going to use, instead of picking the best split, I pick a random split. So I basically split on a random value. And this, of course, increases randomization more. So I would say split at random value. If you actually do the first 2, you build a random forest. So in general, these are the 2 things that are done to build a random forest out of decision trees. If you do the last 2, you build a less known algorithm, but also nice. It's called extra random trees. Like if you ever use sklearn, they are both there. So this is all that there is. What you do, you hear about a random forest, this is how it's built. You built, the key of this type of ensembles. They are called bagging ensemble methods. And bagging here sounds like it should be a real word, but no, it stands for bootstrap aggregating. I don't know why they created this sort of name as bagging, but this is one possible ways in which what you do is that you build a series of independent estimator in parallel. Like each of the trees is fully built, and then you combine them with a simple average to give you a prediction. And again, if the prediction is a continuous variable, you take the average predicted by each of the 3. If the prediction is a class, then you just take a simple majority vote. Very quite powerful. I've decided that I'm not going to go into this, but there is sort of a neat formal proof that you can do that at least for the mean square error loss, you can decompose the loss, the generalization error, so how the loss behaves on new data, as a sum of 3 things: the noise, the bias, which is squared, which is the average deviation between your predictions and the true values, and the variance, which is just the spread around the predictions. And you can actually show that this randomization always decreases the variance. Of course, it's not a win it all, right? Because when you decrease the variance, you also increase the bias, because when you randomize each tree, you are adding stochasticity, and so the accuracy of the single tree will typically decrease. What they're trying to do is like playing with this, so hopefully you can get to a combination where the variances decreases more than the bias increases, and so this overall can improve your test scores, making them smaller. Okay, so this is one type of things that you can do with decision thing, one type of ensembles. It is, however, not the only one. And so I will briefly tell you about the other possible way of combining decision trees. So I'm gonna just leave that part there. And here we're not randomizing anymore, but we'll leave the bugging methods there. Okay, so there is another thing that I can do to ensemble trees. And so let me put them here. And these are called boosting methods. And these are sequential methods. So you see in random forest, I build a bunch of like independent models, and then I combine them together at the end. In this case, what I do is I actually create a sequence of models that I correct stage-wise. So I have my tree, right? As we said, this is like a simple deterministic process. And so this means that basically I create my stage 1 model is something that gives me, output the predictions for this variable. Then the next thing that I do is that I calculate the residuals. And the residuals are simply the difference between the prediction of my model and the real value. Okay, now the next step, what I do is that I make a new model, but instead of predicting my original value, I try to predict the residual. So I change the target of I still use a simple decision tree, but I change the target. Okay, and then at this point, I have my new model, and I built, let's say that this is h of x, the model that predicts the residuals. And then I have my stage 2 model, which is the sum of my stage 1 model and the one that I just created. And then I calculate the residuals of this model. And now I predict the residuals of these models and I add them to here. So you see, this is a model in which every time I look at how I'm doing, I calculate where I'm not doing well, and I try to make a model to predict that. Now, why does this work? Well, I'll try to show you, but the nice things about this is that it works with very weak learners. Remember, when we're talking about the randomization for random forests, even in a simplified version, we said, okay, like I need my base learner to do at least better than random. Okay, this is a model that can work also if the base learners are very weak. And to show you this, I'm going to use my mystery content board. So let me see if I can bring it there. Okay, I hope you're very excited for this mystery content. So let's say that I want to make a regression model, right? It's a simple one-dimensional model because this way I can, I can show you both the feature and the target. So it's not a crazy function, but it's a function that is constant here, and then it goes down, and then goes up and down with some scatter, right? And I want to do it with the simplest possible tree that you can imagine, which is a one-split tree. Like, I'm not allowed to make many partitions. I can only do one. Which, I mean, it's convenient because I only have one feature, but I basically can decide, okay, I can only ask one question. And this type of trees are called stumps, although I don't like the word, I prefer baby tree. So here, we have to make a prediction for this model. And so a one-split tree looks like this. Like basically on one part of the data, I predict the mean. And on the other part of the data, I predict the mean. And the criteria, this is not obvious. You're like, why don't you make a line here? The point to remember is that I want my partition to be as large as possible. So I'm still going for the things that gives me the lowest scatter on each partition weight by its volume. It turns out that it's this one. Okay, now I want to calculate the residuals of these models. So for the residuals, I have to take my prediction, subtract the points to the left and to the right. And this is what comes out. Like I still have sort of a constant, but because my function was over predicting, now I have that this is positive, and here I have some oscillatory behavior with more scatter around 0. So now I have to make a model to predict these residuals. Right? So I make my model. The model turns out to be this one. Now, in this case, it was convenient to get this almost right. And here, this is just, ends up being something which is slightly negative to catch the mean of these points and these points. Now, what do? I have to add the two models together. So I don't know if you remember. Well, let's say that, here we have something that was, like a bit negative on the left side and positive on the other side. And here, I'm summing something that is positive here and something which is slightly negative here. So it turns out that the sum looks like this. And so now I'm able to catch this one. And then here I have this behavior, and here I have this behavior. Now I calculate the residuals of these models, which is this one, right? And then I have to fit this model still with the one-split tree, my little baby tree. And these are, this is the model that best fits the residual. So notice that here now when I sum, I'm actually losing a little bit on the left side because I had something that was already kind of a 0, and now I'm adding something that is slightly negative. And at this point, I was kind of tired to draw, but the thing that I want to show you is that if you do this long enough, even with my very simple base learner, the one-split tree, what you get is that you get the ability of predicting with a constant, because this is what the decision tree does. In each partition, it outputs a constant, right? Either a class or a constant. That sort of like can follow the data with arbitrary accuracy. And so while randomization ensemble algorithms, such as random forest, traditionally, they're used to lower the variance. Again, traditionally, because this is not strictly correct, but these are often used to lower the bias. So to make simple algorithms able to do things with higher accuracy. So now we have unveiled the mystery content. I want to tell you another thing that for me, I think will never not be mind-blowing, which is, this hopefully convince you why the combination of these can be more powerful. The other things that I want to tell you is like, why is this idea of fitting the residuals convenient? And so the idea here is that, let's imagine that I have my loss function. And let me make it the mean square error. 1, because it's simpler. 2, because it's the only one that I know how it works. And so let's say that here you are somewhere in parameter space or feature space. Okay, and so I'm here. And as you imagine, I always want to move towards the minimum of the loss function, right? This is my goal. And if you've seen an algorithm like this, this is often called gradient descent. The idea that I want to take a step along the negative gradient of my loss function in order to move towards a minimum. Well, if you write down the MSE loss, I'm going to do it in white because this yellow gives me a headache. Right, the MSE loss is just like the sum over all the possible examples that you have of the vectors of your predictions for all the objects minus the vector with the true values and squared. And so if you actually take the derivative of this with respect to your predictions, you can see that this is proportional. This is like 2y squared plus 2y pred squared minus 2 the product of these two. And so the derivative with respect to a y pred is proportional to 2 times the predictions minus 2 times the true values. And these are the residuals. So the idea is like every time that you fit the model to the residuals, you're actually taking a gradient descent step towards the minimum of the loss, at least if the loss is the mean square error. But the whole idea of these boosting methods is that you can rewrite them for any loss. You just, instead of fitting the residuals, you fit the so-called pseudo residuals, which are the derivative of that particular loss with respect to your prediction. And so this is, in general, why they work. Let's see, what else do I have? Well, 3 minutes. So let me just leave this here. And the last things I want to tell you is, now that you know everything about ensemble of decision trees, and the idea is like, what can you do with them? When are they useful? So just, in the spirit of decision trees, I'm going to make a split where, yes is on the left and no is on the right. So I'll tell you the no because it's easy and also because it's important. So as we have noticed in the beginning when I told you, I bet that, like many of you wanted to build this decision tree with some combination of stellar mass and orbital period, or like of stellar mass and distance, right? And this is something that is forbidden in decision trees. You can only work with your original features. So basically the one thing that you cannot do with this data is representation learning. If you are interested in learning from the data what features are important or informative, this is not something that will work. And so traditionally, I think that the way that we write it is that they work really well on tabular data, but I don't like it so much because we can always arrange data in a table. What does it even mean? The important thing here is that I cannot learn features with tree-based methods. Right? And there are many cases for, when you process things like images or like time series or other type of complex data where what you're interested in is an emerging representation. So for this, they're not good. But if you have data that are tabular, which means that you have a space of features that you are confident in, then this actually perform as well as deep learning method. And this is, I think, Sebastian Rashka has a lot of work on these. Many other people, but I think this is the one that I'm most familiar with. So he has sort of like a repository of like data set and problems where you can actually see that in many cases, this is something that work as well as a neural network with additional advantages of being fast. And I wouldn't say fully interpretable. A single decision tree is definitely interpretable. You can literally ask what kind of questions it asks to get to a decision. When you do an ensemble, this is a little bit trickier, but still, it is like a fairly transparent method. And then the last thing that I want to say about this is that another thing that you can usually do with this is get a sense of which features are important. Sometimes this is called feature ranking. We don't like this. We'll say importance. So just in general, if you have a tree, you can imagine that the features that are more important will be chosen more often for splits. Right? So there is this very basic idea that in a tree or in a forest, anything that has a tree involved, you can actually pick each of your features and go and look at how much decrease of impurity is associated with that feature in every single node where it appears. And this gives you an idea of which features are most important. The reason, like, I don't believe you can really trust the ranking, because as when features are correlated, they split importance, and so this is problematic. But I think, you know, what you want to do is to find a set of features. I think they actually work okay. And these problems of correlations, anyway, I don't think that, you know, we really know how to solve it much better than them. So I feel like, you know, for a baseline, you want, you know, to start from a large data set and find a subset that can work. I think they're quite powerful. All right, I think this is more or less it. I want to tell you to buy my book. If you want to have more content, it's now available for pre-order. Also, you know, if you or someone who is dear to you want to learn basics of machine learning, here at Flatiron, we have like an online course, which you can find at openlearning.flatiron.org. And, you know, we are very grateful for the support. It is like free, it is open to everybody. And we're actually now working, and again, thanks for the support, on making it available in Spanish. So there will be a new course called Aprendizaje Automático para Física y Astronomía. We have some of the people here who are involved in developing. So we're hoping to also make it available later this semester. And that's it. Thank you.